Hello everyone, welcome back to AlphaBeta. This is episode 5. We're going to be talking about delta, one of my favourites. Let's get into it. Delta is the fourth letter in the Greek alphabet. The ancient pronunciation gives a D sound, like in delete or day, whereas the modern pronunciation is more of a TH sound, like in then or there. Delta comes from the Phoenician letter dalet, which I'm sure I've mispronounced, and the Cyrillic and Latin letters for D are composed from delta itself. Delta is used an awful lot in science. It's used in calculus to show the rate of change or the difference operator. So when you have two variables, perhaps you have y and x in a graph, you can find the gradient of whatever graph you have by taking y2 minus y1 over x2 minus x1, and you can represent this by using delta. It's also a big component of calculus where you have dy by dx, where you're finding the gradient at one point in a graph, which is phenomenally useful. Another big part of calculus is signal processing, where we find arguably the most important transform of them all, for signal processing at least, the Fourier transform. And the Fourier transform was initially built basically to model a wave where there was two different temperatures along a piece of metal. So you have a metal rod where you have temperature X and temperature Y, and you have a gradient. And to model the heat dispersion through the pipe, or the rod, whatever material, you effectively have one temperature like this and one temperature like this. And so to model this, you effectively form a square wave. Now you can use the Fourier transform to produce a square wave by simply summing each odd frequency, where you then divide through by whatever that frequency is. So you would have a sinusoid at frequency 1 Hz plus a sinusoid at frequency 3 Hz divided by 3 plus a sinusoid at frequency 5 Hz divided by 5. This infinite sum then times by 4 divided by pi will give you a perfect square wave. It's actually something that I've shown in lectures that I've run for biomedical engineering students, where we teach signal processing and how we then generate a wave. So we produce a composite wave just showing the concatenation of different frequency sinusoids basically pushed together into one big wave and so on. And then we take the Fourier transform of these to show the frequencies and how we can show one wave with multiple different frequencies. It's also where we get into the spectrogram, where we can see the frequency increasing through time. And quite interestingly, when you take the Fourier transform of a square wave, you have this kind of decrease, because obviously as you're dividing through by n, where n is the frequency, you're then drastically decreasing the power that that frequency has present in the signal itself. So it's very cool seeing this big spike at frequency of 1, and then it decreases down exponentially. So on the subject of delta being used for change, I've also found out through some research that delta is used in study of genes, where there is gene deletion. So there will be the code for the gene, and then there will be delta, then whichever gene has been deleted from that DNA sequence. So moving back to calculus and the ablation in particular, the symbol for the Laplace, or the del function, is the capital delta upside down, so it's like this triangle upside down, which is very interesting. I quite like it actually, and in fact delta was one of the first Greek letters I had tattooed. I think it was the 4th, and then I think I got nabla around I think it was the 6th or 7th that I got tattooed eventually. And I'll show these upcoming when we hit a subscriber goal. I think perhaps if I set the goal of 100, to do a small tattoo tour down my arm. So that's delta. I hope you enjoyed. If you did, please consider leaving a comment and subscribing, and I'll put up 2 previous videos if you haven't watched any of those. Thank you very much for watching.